Okay, so let's welcome CJ Lai from Academia Sinica, and he will be giving talk on Wreath products, Schur's dualities, and quasi-hereditary covers.
Yeah, thank you for the invitation organization. So today I'll talk about a joint work with Jen Nakano and Ziqing Xiang. He was a former PhD student at the University of Georgia, and I personally was a postdoc here 2 years ago, and it's my pleasure to be back. So first, let me explain what do I mean by a Schur duality. So I'm talking about the double centralizer property between certain algebras U and H. And so I also consider the following object in the diagram. Typically, we fix, say, the rank n is greater than the varying number. So firstly, we have a algebra of rank n up here, acting on some UH bimodule. So this is usually realized as the tensor space. And then on the other hand, we have an algebra of rank D. And then you can take the action from the right-hand side, find the centralizing partner of this right HD action, and then you get a Schur algebra here. And moreover, this can be realized using the notion of dual coordinate coalgebra. So maybe I should write directly an isomorphism here. So this is the deep degree component of the dual of the coordinate coalgebra. So for this complete diagram that I have, by Schur duality, I have several favorable properties. So the double centralizer theorem tells you that the bimodule now decomposes into a tensor product, direct sum of tensor products of irreducibles. So you have a Schur functor. By taking hum of this that goes from one module category to another, matching those irreducibles. And for the coordinate construction, I mean, these categories are actually isomorphic. And you can talk about degree D AN co-module. So this makes it possible to study the representation theory of all these objects altogether. And there are many examples of this picture, say in type A. This is the quantum Schur duality by Jimbo. And these objects are, for example, partial Wangs, quantum general linear group. And the algebra U here is the Drinfeld-Jimbo content group. And this subjects to Dipper-James q-Schur algebra. And this is a tensor space of the natural representation of the quantum group. And then you have the Iwahori-Hecke algebra here for the symmetric group. And for type B, this is also possible to define such Schur duality in many ways. Let's see, what do we have here? So I want to mention that there's a way to define all these objects for a different quantum group, but this is not what we want. We want to keep the Hecke algebra on the right-hand side. Say we are looking at a Hecke algebra of type B. And then this does not correspond to a Drinfeld-Jimbo quantum group. Instead, this is the I quantum group or the co-ideal subalgebra from the quantum symmetric pair due to Bao and Wang. And then you have now a hyperoctahedral q-Schur algebra. Say, I think this is first due to green. Then you can realize all these algebras using a co-ideal co-algebra due to myself, then Nagano and Ziqingxiang. So this is the usual. This is the Schur algebra in the usual sense. So the next question is we can actually talk about this Schur functor more. So let me start with some notions. Say in rep theory, it is nice to have a highest weight category to work with, and one property that we have is a highest weight category is equivalent to a module category for a quasi-hereditary algebra. So this is the highest weight category in the sense of Klein partial Scott, which I will provide detail. I won't provide detail for today. I'm saying this is equivalent to that. This is a module category for some quasi-hereditary algebra. Again, I won't also provide the definition. So I just want you to know that for quasi-hereditary covers, which is in my title, I'm really looking for something that relates a highest weight category to a module category. And it is a theorem by Ringo that every algebra has a quasi-hereditary cover, which means a functor going from a highest weight category to this module category. So this is defined by taking the hum of a projective module from this highest weight category to the module category of this algebra. And then you have some things to check. For example, the harms are the same after taking the functor. And this is also why this is called a zero cover, because this is basically x, you check x0. And then the upshot here is, although every algebra has a quasi-hereditary cover, a zero cover, this zero cover is usually too large. So it was answered by Rouquier. He actually has a unique quasi-hereditary cover that is nice and small enough. In his notion, this is called the one cover. So by one cover, this is just a zero cover that satisfies additionally x1 isomorphism. So we have examples, say, from the work of Hammer and Nagano.
Sorry, CJ, you actually need conditions on your module M and F. Is that correct?
You do. So the M and N are, I think, modules admitting delta filtrations, but I don't want to go. I didn't even talk about delta modules in the high-square category, but you're absolutely right. Right. So some parts of the talk will be hand wavy-ish. Sorry about that. So they show that the Schur functor for the type A Schur algebra module category to the Hecke algebra module category is a one cover when the multiplicative order of Q is greater or equal to 4. And there's also work by Ginzburg-Guay-Opdam-Rouquier, saying that the KZ functor from the category O of the rational Cherednik algebra to the Hecke algebra module category is, I think, zero cover in general and one cover at special cases. So, I mean, here, W can be a complex reflection group. And HW, boldface, is the corresponding rational Cherednik algebra or rational Daha. Okay, so now if one can ask if the two functors coincide, or if there's a commutative diagram between the three module categories. In other words, we can realize the category O of rational Cherednik algebras using module categories for of Schur algebra, which is a finite dimensional algebra and usually can be realized concretely in many ways. Say the combinatorial approach using Q permutation modules, or the geometric approach using counting over partial flag varieties. So for, say, a complex reflection group, what is this Schur algebra? With the Schur duality I mentioned earlier, such that the following diagram commutes. For type A, this is done by Rouquier. Basically, he proved the uniqueness theorem of one cover and then checked that the Casey functor is a one cover. So this must coincide with the usual Schur functor when you combine the results of Hammer-Nakano. And for type B, this is recently solved by myself and Nakano Xiang. And this is this question is in general open beyond type A and B. So I know there are multiple notions of Schur duality beyond A and B, but to my knowledge, there is no one cover, or not yet to be known. But anyway, so I would say a key idea in this type B proof is a compatibility of Schur dualities of type A and type B. So you have a, say, Schur algebra and the Hecke algebra of type A acting on the type A tensor space. Sorry, type A tensor space. And then you have an inclusion on the right-hand side, this Hecke algebra inside the type B Weil group, sorry, Hecke algebra of type B. So you can have another Schur algebra acting from the left-hand side as a subalgebra of the type A Schur algebra. And then you have one more ingredient, more or less motivated by from the Morita equivalence between the type B Hecke algebra and the type A Hecke algebra. So this is a product of some type A tensor. Sorry, this is I. So I'm being very sketchy here, but I want to convince you that this is a crucial step. So if we want to generalize this, we want to attack this problem for other type, it might be very useful to look at a replacement for this compatibility and also this Morita equivalence. So for the next case, we want to look at type D, which is the complex reflection group of type G 22D. So for this, you have the modular equivalence by Hu. Actually, let me do with only the difficult case. So for different parity, you have a easier multi-equivalence or a more complicated multi-equivalence. So when D is an even number, this is the complicated case. You have a multi-equivalence that goes from this to some algebra plus a type A tensor product. So this AM is part of the quantization below. So you have a tower group that can be quantized into tower of Hecke algebra, sort of. So you have a Young subgroup of the type A Weil group, and then in between there is a Wreath product M sigma m by sigma 2. This is probably not the usual Wreath product you're familiar with. The usual Wreath product you're familiar with is the larger group, that is the type B Weil group. And then you can also embed the type D Weil group inside this guy. And then you can quantize all these groups to say Hecke algebra tensor. And this is the type A Hecke algebra, the type B Hecke algebra. But in order to make it compatible with the type D inclusion, you want to take the 2-parameter type B algebra and specialize the parameter associated to the special node to 1. And here, this is what I mean by whose Hecke subalgebra. This is a natural quantization of the Wreath product. And for the next, I think, 20 minutes-ish, I'll be explaining some properties of this Hooke Hecke algebra. But before I do that, are there questions so far? Cool. Oops. Okay, so let us do some setup of this Whose algebra. So you can, it has to go with some computation within the type B Hecke algebra at some special specializations. So you need to start with a UC Murphy element, U plus or U minus. This is a product of factors of this form, q to the power I plus or minus t I to 0 to I. So this is a shorthand for the product of simple generator ti, ti minus 1, all the way to t0, and then 1 back to ti. Oh, by the way, so I'm using the label like this. So this is the one corresponding to t0, t1, and so on. So this is now a element in the largest Hecke algebra of type B, but with specialization capital Q equals to 1. Then we can define an element H. This is the unique element in type A Hecke algebra, such that this U plus times some element I will explain later, U minus is inside this. So this looks a little bit annoying. So let me explain what happens here. So this H here is the type A Hecke algebra, and this pi is the Hecke algebra element corresponding to this very special permutation, swapping the first chunk and the second chunk. So when you look at this, what does this say? You have, when you expand, say, the left-hand side, you get a bunch of sums of products of Hecke algebra elements. You want to collect all the elements involving, say, UB greater than M. So you're collecting all the unwanted one, and this is like doing a division, but in a very formal way. And there is a unique element in the type A Hecke algebra, so that you can write your product uniquely. And we'll see some examples shortly, but I want to say that there is no like easy way to describe this. I think it's maybe better to look at one easiest calculation, say for m equals to 1. U plus or minus is really just one single factor, 1 plus or minus t0. So you really want to expand, say, 1 plus t0, t1, 1 minus t0. Oh, by the way, so pi here is t this, which is t1. So you get 1 plus t0 h1 plus something that can be expressed like this. So the question is to figure out what is this unique element in the type A Hecke algebra. So this is actually not too bad, because you look at this. You want to find a term so that you have 1 plus t0 times q plus t1, t0, t1 at the end. So you can really just try to find a term that is q plus t101, and then you offset this, so you can find a concrete way to express this h1. So when I multiply out this, I get t1 minus t1 t0, but I want to really find something that is of this form. So I multiply an additional t1 at the end, but I need to offset that, which means I have 1 plus t0 t1 plus something of this form. And there you have one term that offsets again. So with this, the unique element we're talking about is T1 plus Q, T1 inverse. So even with this smallest example, this is it takes quite a bit of computation. But this gives us the extra generator that we need to define whose Hecke subalgebra. So we have an anti-automorphism. The Hecke algebra sending each simple generator to itself. So you just reverse the order, and whose Hecke subalgebra is generated by T1 to T2n, except for Tm, and also this H star. So this is now a subalgebra of the type A Hecke algebra. Oh, by the way, so here the anti-automorphism does nothing to just T1. So H1 is H1 star, and then you can get something like H1 squared to some central element by direct calculation. Okay. So further remarks on this weird element H star. So it is unclear if there is a explicit formula for H star. So I think this is one of the obstacles for people to study these whose Hecke subalgebra, because when you try to do the direct computation from the very definition, this is easily very complicated. Even for H2, you get a bunch of terms like this. This is T1, T2, sorry, T2, T1 plus T2 inverse, T1 inverse, T3, T2 plus something similar. So it seems that you have a pattern here, but there are more terms that vanish at the specialization q equals to 1. And for this part, yeah, I honestly don't know if one can observe any pattern. So by looking at this, you have some observations, say Hm at q equals to 1 equals to 2 to the m times the special permutation we talked about. And then what else? Oh yeah, so remember from this example, we are dealing with this computation with inside this type B Hecke algebra. It is also unclear whether we can obtain this element without using the UC-Murphy element or the type B Hecke algebra. Okay, so I hope this gives you some idea of this whose Hecke algebra, but we will talk about soon some other approach that we don't need to deal with this actual complicated computation. So what we need now is some presentation, alternative presentation. So from the previous example, we saw that H squares to a central element, and this phenomenon actually holds for larger n. There's a unique central element in this, satisfying some random equation. So probably we don't want to pay too much attention on this. But what's more important is this H star square to this unique central element. And also there's some other relations hold in inside the Hecke algebra of type A. So when you try to swap H star with the simple generator, you can almost do that, but you will need to modify the subscript. So what does this tells us? This is almost like an abstract generator relation presentation, but this is not really a relation because this z is not a coefficient, and this is some element in the center of the type A Hecke algebra. But we'll see that we want to really treat this a squared equals to z as a quadratic relation, as in the typical Hecke algebra. So in the typical Hecke algebra, you get something like this. But we really want to treat this equation with coefficient in the center, some generalization of the quadratic relation. And by the way, we have now the AM, the whose Hecke algebra is just a group algebra of the Wreath product and 2. So maybe it's better to realize this using some, how should I say, or maybe I just give you some visual aid. So if you're not so familiar with the Wreath product, you can think of it as a automorphism on some rooted tree. So this is going to be the automorphism of rooted tree from 1 to 2n this way. And then you have some permutation that swap the entire trees of height 1. And you also have these simple transposition modulo Sn. Okay, I hope this helps a little bit. Okay, so the final part is to now define a Wreath product for algebras that include this whose Hecke algebra as a special case. So recall for finite groups, you can take a Wreath product of the symmetric group as a semi-direct product, And then if you write the elements out, this is a D tuple of elements in G combined with some element in the symmetric group. So the multiplication of the Wreath product is determined by equation like this. If you are multiplying two elements in the Wreath product, you need to know how to swap W with G. And the typical way is to do that, but you also have your permutation act on the subscript. So this Wreath product admits several quantization in literature. For example, the Ariki-Koike Hecke, Ariki-Koike algebra or cyclotomic Hecke algebra is the Hecke algebra for the Wreath product of a symmetric group by a cyclic group. This can be realized using a bunch of generators. So pictorially, you have a rooted tree where sigma m permutes the higher level, and x is the generator that permutes every letter by one on the first branch. And then this, you have a cyclotomic equation. And this V's are just parameters. And you have also the usual quadratic relation plus more. I mean, more relations. And there's also a degeneration, a quantization by Wan and Wang. So you obtain the degenerate affine Hecke algebra for such a Wreath product. So by degenerate affine Hecke algebra, you have more juicy Murphy elements in the generator, and you have relations corresponding to these extra ones, but that's not our concern for today. And what I'm trying to say here is the relation you're modding out is of this form. 0 equals to ti squared plus, minus 1. So this is a degenerate quadratic relation compared to the usual Hecke algebra. And you have some relations that quantize this. So when you swap a tuple, you are, maybe I just do it this way. You just interchange the factors. And there are, of course, more relations. And then finally, what I want to say here is you can actually do this for the Hecke algebra. So we can define something that quantizes the Wreath product sigma m by sigma 2. So you take the tensor product of a smaller Hecke algebra and then an extra generator. This is actually our H star. and you can mod out similar equation, but you replace this h squared to z like that. So you do have a coefficient in the center of the former part of the definition. And the upshot is we have defined a possibly non-degenerate Hecke algebra. That is roughly the default tensor semi-direct product with a Hecke algebra of type A with quadratic relation Ti squared lies in the center plus some lower terms.
Yeah, so you should make it clear that it's not split though.
Sorry, what's the question?
You should make it clear that it's not a split extension, highly non-split.
All right, so this is so I think what Dan says is usually for finite group, you can realize this Wreath product as a group extension, and this is the unique split extension of groups. But this Wreath product is not a non-split extension, and it actually we have the flexibility. You can this can be defined as any nice extension of algebras. But I will leave the I'll leave for now. Okay, so some final remarks, and we can now quantize all these. We have a definitions of the algebra Wreath product between algebras, and then what we are going to go from here is we have that this is well defined and contain the whose Hecke subalgebra and also the cyclotomic algebra as special cases. We have the Schur duality for this tower of algebra. So this is maybe I should start with the right hand side. This is what we had. Oops. And we can define the corresponding Schur algebra for the whose Hecke subalgebra using a similar compatibility argument. And then the upshot is this gives us some evidence to construct a one cover from the Schur algebra of type D to the module category of the Hecke algebra of type D. So this S involves the Schur algebra correspond SA here, but I don't find it useful to give you the construction. So I'll just write something vague here. Okay, so maybe I am running out of time, so I'll just comment further. I think this idea helps in finding the one cover for other complex reflection group. So in type D, this is like not just a random isolated case. You can actually consider the complex reflection group of type G, say P, D, so that you can expect a multi-equivalence that generalize the type D multi-equivalence. And then maybe this leads to the construction of one cover for the corresponding rational Cherednik algebra that in turn realize these rational Cherednik algebra category O using some concrete finite dimensional algebras. Okay, I think I'll stop here.
Questions? So if there's no question, then let's thank the speaker again.
Maybe I should make a point. So this is a historical point. So can you back up your slides, CJ?
So where you want this?
Yeah, I think you kind of alluded to this. So I mean, I just want to keep backing up your slides. Go on. Yeah, stop there. Right there. So in some ways, that's how rational Cherednik algebra started out, was with this GTOR paper. And their idea was to construct like q-Schur algebras for other types. So they wanted the analog of q-Schur algebras for other types. Those are the motivation. Constructing this KZ functor as a Schur functor between. A lot of people will just like study rational Cherednik algebras, but they won't say where they're really coming from. This is actually the paper that kind of started off the game. You agree, CJ?
Of course.
Okay, good. Yeah.
Okay, is there any other comment? Okay, then let's thank the speaker again.
Yes. Hey, John.
Hey, CJ.
Yeah, good to see you again.
Good to see you too.
Yes. Yeah, I